continue to explore the properties of the Schwarzian solution. So recap on what we did. So first, we derived the solution. The solution is Einstein's field equation in vacuum. We're looking for a solution which is static and isotropic. We found, after some lengthy but algebraic in nature, so nothing that was conceptually new, we find the solution, which is ds squared in minus 1 minus 2gm over r c squared. I'm putting down the c just to make sure that everybody's with me. Plus 1 minus 2gm over r c squared minus 1 dr squared plus r squared d omega squared. And I argued that there is a theorem which is called Virchow's theorem, which says this is the only theorem, which is the only static and isotropic solution of Einstein's equation in vacuum. And that comes a point that the last, just when finished, there was a question that you asked me about other solutions. So I told you that there are not very many solutions that are known to Einstein's equation, because it's a non-linear, then the fact that we know two solutions does not mean that any linear combination of them is a solution. And I told you that for Einstein's equation in vacuum, there are three solutions known. So one of them is the Schwarzian solution. The second is the Nordstrom, and let me a second to remember his name. Solution for charged particles. So if it's charged, then it's not a vacuum. And the third one is a Kerr solution, which is a rotating solution. The difference is rotating means it's not isotropic. So that answers the question. The Kerr solution is a solution to Einstein's equation in vacuum, but not an isotropic solution. Yes?
For the other cases,
There is
there is terms from them that say that the only solution for those cases, or it can be other solutions.
I'm not aware of that. So it's very well possible that there are many other solutions to Einstein's equation which are simply not here. And I mentioned to you that observationally there are very good reasons to believe that we don't expect to find any charged black holes in nature, because if they are born charged for any reason, which I cannot see why they would be born charged, because black holes are born when stars collapse, and stars, as we know, are not charged generally, but maybe some objects like that exist. And what will happen is that there will be a huge potential, electromagnetic potential barrier, which will be attracting all the free charges in the vicinity of the black hole, which will immediately discharge it within time scale comparable to the time scale of formation or light force down to the black hole. So in nature, we don't expect to see charged black holes. Rotating black holes we do expect to see, and we actually do see. As you know, I'm sure you've heard that the last Event Horizon Telescope results came out just 3 years ago, which actually show if you have not then just do EHT results. We'll see them. Okay, but slowly, we're not talking about black hole here. We're talking about the Schwarzian solution. So the first we derived the solution, and we said this theorem states that this is the only static and isotropic solution that one can find for Einstein's equation in vacuum. Then when we looked at the solution, we said there are two interesting radii here. That something must happen. So one is r equal to 0, and the second is r equal to 2gm over c squared. Obviously, when r is equal to 0, we cannot divide by 0. And when r is equal to 2gm over c squared, here we get a 0. We can still live with that, but here we get 0 to the power minus 1, which is ill-defined. But then I argued that possibly this is not something to do with any physical issue, but something to do with simply the choice of coordinates that we have. In an analog way to the choice of coordinates of describing the space, the flat space we can choose, like describing Cartesian coordinates or spherical coordinates. And I argue that there is a way of finding if there is anything special happening, and we were looking for some scalar, and the scalar of interest is called the Kretschmann scalar. Scalar R, which is K, whose name is R, and rho sigma mu nu, rho sigma R mu nu rho sigma, and I argue that this is equal to 12 g squared m squared over r to the power 6. And that means that r equal to 0 is a real singularity. And it's not a real singularity. It's a singularity. In the sense that I can, and we will, find different sets of coordinates, not t, r, theta, and phi, in which nothing special will happen in the radius. I'm not going to describe this right now. We'll have to wait when we discuss black holes. And in a basic sense, really nothing special happens there. So if we go now to the physics, if you happen to travel inside the black hole, there is no problem getting in. You will not even feel it. You will not even notice that you fall into a black hole. Of course, the problem will be you will not be able to come back. But again, the time will come when we discuss that. And then I said that this is nothing to be worried of in the realm of the solar system, because if we look at the Schwarzschild radius of our sun, then the solar system now the mass of the sun is 2 times 10 to the 33 grams, which means that 2gm sun over c squared is something like 3 times 10 to the 5 centimeters, while the radius of the sun is about 5 orders of magnitude larger than that, meaning that this solution anyway is not going to be only valid outside of the sun, because inside the sun it's not equal to 0. And the team knew there was 0, so we don't really need to worry about that in our solar system. We need to have objects which are extremely compact, that all their mass is enclosed within the Schwarzschild radii, and as I said, we will discuss black holes, but not yet. Then it is worth giving it a visualization, right? I did tell you that if you think of this as this metric would look something like that, right? Very far from the center, so this is r equal to 0 basically, right? So very far from the center, there is nothing. This is r equal to gm over c squared, and the metric is curved when you get closer. Yes.
יכול לחדד על ההבדל כאילו בפרשנות של טנזור ריצ'י לטנזור רימן, כי פה אנחנו רואים שטנזור ריצ'י הוא 0, למרות שיש פה פומביות מלאה באזור, כאילו גם בוואקום, אבל טנזור רימן הוא לא 0, כי אם הוא היה 0 אז זה היה בכלל.
The Riemann tensor is a 1-3 tensor. It has many components. The Ricci tensor, you obtain that from the Riemann tensor by contraction. And so the Riemann tensor, the Ricci tensor has very much fewer components. So it does not capture all the physics basically, or all the geometry inside. You cannot really compare them because they don't live in the same space.
אני מתכוון כאילו, איך שאנחנו מפרשים אותם, כאילו בשיטה הגיאומטרית, כללית.
The Riemann tensor tells you everything you can know about the curvature of space. Ricci is more degenerate. It's like the Ricci scalar. It gives you some information, but doesn't give you the entire information. I'm not sure that I can give you a better answer than that. I would say, the way it really evolved, like Gauss solved this thing for two dimensions surfaces. That's called a Gauss curvature. I can give it to you in one of the problem sets about calculating Gauss curvature for two dimensions. Then Riemann, which was his student, was asked, and what he did was to extend that to n dimensions. I'm pretty sure that by that time Gauss did not think about 4 dimensions space-time. This was become evident later. I'm not sure I have a simple way of telling visualizing what the difference would be. If you can't think of things I cannot visualize it myself right now, then I won't just give the answers which are incorrect. Okay. Then the next thing we did was,
The capital L here is the Staatsschwierigkeit beschreiben.
There's no Schwarz. This is the Kraftmann scalar. This is just Kraftmann scalar. The scalar depends on the location it's in the space. This is just a way of telling you that this scalar is for every r you get some number, except for r equal to 0, where it's close. Then we said, okay, let's look at trajectories of particles. So motion of particles Really what we care about is test particles. So particles that their existence does not affect the metric. And then we said, okay, we can write down the geodesic equations, which turn out to be lengthy to solve. Then we said, instead of trying to write directly the geodesic equations, let's make use of the Killing vectors. We saw that Killing condition tells us k mu. So if k mu is a Killing vector, then k mu dx mu over d lambda is a constant of motion. That's one thing. And then we also make use of the metric compatibility, which we wrote down in the form epsilon is minus g mu nu dx mu over d lambda dx mu over d lambda, where epsilon is 1 for massive particles and 0 for massless. In generalized that, we think of epsilon equal to -1 this will be only for particles that travel faster than the speed of light. So let's ignore that. And then we said, okay, so we have, for this metric, we basically have 4 killing vectors. One is associated with the time symmetry, so time translation. And 3 associated with the angular symmetry, so rotation basically. So the time symmetry gives rise to conservation of energy. The rotation gives rise to conservation of angular momentum. So we wrote down the first vector, this is energy. And the killing vector was k mu 1, 0, 0, 0. And then k mu dx mu over lambda is 1 minus 2 gm of r dt over d lambda, which is a constant of motion, which we call E. You can simply think of it as a constant of motion, it doesn't really matter. And then for the rotation, we said we can think of it as rotation around each of the 3 axes, but easier to think of it as one vector which has a magnitude and direction. The direction specifies a plane in space, which all the particles are orbiting around. So similar to think of it as the solar system. It's the same thing basically. Right? All the planets, because of conservation of angular momentum, all the planets are rotating, orbiting the sun in a constant plane. So we can call that the just forgot the name. Equatorial plane. So 2 for direction. Let's set the equatorial plane. And 1 for the magnitude. So without loss of generality, we can say this is going to be along the x direction, along the z direction, sorry. So I'll say that the L mu will be 0, 0, 0, 1. And that means that L mu dx mu over dt lambda so just r squared sine squared theta d phi d lambda. Since sine squared theta is just 1, so this is just r squared d phi over d lambda is another constant of motion, which we call L. So not too bad. Instead of solving, when we wrote down directly the geodesic equations, we got 4 coupled second-order differential equations. Now we add some constants of motion. Plus we have the metric compatibility. Okay, I think this is as far as we managed to go through last time. Any questions about it? Any further questions?
My question about rotation was more of where is the point in our workflow where we change the logic? I mean, if in what exactly step we need to account this rotation?
We wrote down isotropic. Right? Yes. So when we say isotropic means that we make a separation of R and omega. Right? So it's one of the first steps actually. When we wrote down the metric, we said we want an isotropic metric. If we remove that requirement, then we cannot do that. We cannot make this separation.
And isotropic means that every direction is
Isotropic means it looks the same in every direction. yes. If the sun was rotating very rapidly, right, then you have the equatorial plane, and you have the plane above that, and it will not be the same. Yes.
L mu and K mu are satisfied the Klein equation, like it's trivial, or you need to show this?
You can show it right away.
Okay.
You can simply put it down here, and you'll see that immediately that this satisfies the Killing equation. Right on L is d phi. Just plug it in here, and E is dt, and you can see that it satisfies. Remember the Killing equation, k nu common nu plus k nu common nu. So right away. Okay, I think actually you're given a homework to do some playing with Killing equations, so you can get the feeling. Okay, so the next thing we're going to do is take this metric compatibility, which is written here. This is the metric compatibility. Let's write down the metric compatibility specifically. Move the minus over here. So you get the g mu nu dx mu over lambda dx nu over lambda. So g00 is a minus 1 minus 2 gm over r t over d lambda square. I don't have any cross terms here. Plus 1 minus 2 gm over r minus 1 dr over d lambda squared plus r squared. I have here d theta squared plus sine squared theta. D theta is of course 0 because it's a fix, but sine squared theta is 1, so I don't need that, so I only have d phi over d lambda squared is equal to minus epsilon. Just put that minus. That's not bad. That's not bad. Now I'm going to multiply that by 1 minus 2 gm over r. So I have here minus 1 minus 2 gm over r squared dt over d lambda squared, which is minus what? E squared plus, here I just have the r over d lambda squared. And here I have plus 1 minus 2 gm over r. So I have r squared d phi over d lambda squared. So I can simply write this as L squared over r squared. This is just L squared over r squared. Here I have a minus epsilon times, so I'm just moving it back here, so I have plus epsilon is equal to 0. So obviously this is much better than before. We have one equation rather than the 4 we had previously. Also, multiply that, I'm moving the e squared to the other side. I multiply everything by 1/2. So I have 1/2 dr over d lambda squared plus some function should not go v of r, sec in second is equal 1/2 e squared. What is v of r? I'm going to expand that. is either plus or plus 1 or 0. Then we have here minus 1/2 GM over R epsilon plus L squared over 2R squared minus GM L squared over R. Okay. Does that ring a bell? This equation.
Looks like an effective potential.
This looks like a Kepler. Now, although I wrote it down, the way I wrote it down, there is like powers of R, right? On R squared, R cubed. It's not an expansion. There is nothing else here. This is exact. So this equation really. This looks very much like a Lorentz equation of motion. Now don't get confused, right? The motion is in 3D. Actually, it's in 2D because we said it's in a plane. Right? This only takes, I just reduce it into one dimension. It's R. And I just look at how R changes. Right? I didn't look at how phi changes, right? Just to get a feeling. So let's say this is the source of potential. Like the true orbit will look something like that. Right? But what I care about, the way I reduced it, very similar to what you did in first year, I just look at R as a function of lambda. R of lambda. Lambda 1, lambda equal to 1, 2, 3, 4, 5, 10. Right? So I'm only looking at R as a function of lambda. So it's the same problem that was reduced, was done for you in year 1 in classical mechanics. So very similar to Keplerian, analog to Keplerian. As we said, E basically is a constant of motion and L is a constant of motion. So of course this is just a constant. For potential, we don't care about constants. This is exactly the Newtonian potential. Right? I'm putting epsilon equal to 1 for massive particles. Right? So I'm putting that, this is for exactly the Newtonian potential. This is
Effective potential.
but this is the correction because of angular momentum. Again, you've seen that in Kepler's laws. Up until here, these two terms are identical to what you've seen in Kepler. This is the new one. This was not there. Makes a whole difference. Where do we see the difference? Small radii. When we go to large radii, this will be the one that we could throw away first because it goes 1 over R cubed. Right?
This is really the correction to Mercury, right?
This is exactly the correction. Now, all planets have corrections, but the
Yeah.
further away they are from the sun, the correction gets more and smaller. Okay. Also, of course, this gives us only partial answer, right? Because this gives us R as a function of lambda, but of course we also care about T as a function of lambda, phi as a function of lambda, etc. Theta as a function of lambda is constant. Okay. So let's look at the trajectories. So now we make a distinction between massive particles and massless particles. Let's start by massive particles. Here's the epsilon is equal to. So if I put down the potential as a function of R, 0, 1/2. So now it depends, of course, on L. I can look for various values of L. So first, let's do it once. Let's start with, let's do it for the Newtonian case. Newtonian means I don't care about this term. Okay? So no GM squared over R cubed. Okay. So let's we can simply draw it, right? You can simply ask your favorite drawing code to draw it for various values of L, and what it will look like is something like that. Where R goes to infinity, right? Of course, you don't care about that. It goes to 1/2, right? When R goes to 0, what happens when R goes to 0? But it's divergence upward because of this term, right? So it should go something like that. And then, depending on the value of L, it will look potentially look something like that. This is for L equal to 1, for L equal to 2, it will look something like that. L equal to 3, it will look something like that. L equal to 4, it will look something like that. And so on. Now, before I'm going to draw what happens with the full GR term, what kinds of orbits you have in the Newtonian potential? Right, so you have two general types, one is called closed orbits and one is called open orbits. And what do the orbits depend on? What?
The value of E.
Right, orbits, they have closed, they have open. They depend on the value of E relative to V. Right? Where's the turning point?
E.
Right, so it's a E, or in our case, turning point would be at V of R equal to 1/2 E. And okay, so if the potential is flat, what do we get? Let's say we're sitting right here. That orbit we're going to get? Circular. Just a circular orbit, right? So the orbit will look something like that. If we're increasing the energy, then we increase the energy, then what type of orbit we'll see? Ellipse, right? Which will be bounded between R mean and R max. So if I draw it here, it will be something. So let's say R mean. This will be R max, and the true orbit will look something like that. It will look like an ellipse. It will go something like that. Familiar, etc. Are you familiar with that motion? What do you call the motion of the? It's called the perihelion and aphelion turning points, and they also move. What do we call their motion? You know, Precession, yes. There's no precession. You can learn precession. Yeah, I have
You're
this
asking
for-
in analytical mechanics.
yeah,
No,
this is we're supposed to learn it in analytical mechanics. For a reason which is unclear to me, this part is being skipped. So we'll do, I encountered this problem last year. I didn't realize that. So we'll do a tutorial about precession because we need to know this thing. It's not precession. But for us, so you can see how the orbit will look like. Right? This is how it's being described, and this is what it really looks like. And so these are, of course, bound orbits. Right? They have an R max, R max, and R. What else do I have to say? What if the particle has a lot of energy?
No.
Yes, it can go like that and go back. Right. So what would be the orbit of such a particle? So this is either a parabola or a curve. You all know that? You've seen that? Where did you see that?
Yeah.
You did see it in analytical mechanics?
Yeah.
Just perception. לא ראינו לקיפון, ראינו ניסויים.
Yeah, we saw it.
Did you see a rigid body rotation? Interesting. We did see that. So of course the trajectory, it looks something like that, right? So particle comes from infinity. It's affected by the gravity and go back to infinity.
Yes, we saw.
What?
יותר ראינו.
That you've seen. So this is what this trajectory really means in reality. So the condition for stable condition for a circular orbit is that potential is flat, so the V over the R is equal to 0. Now you can get that by simply taking the derivation of the potential. Then the radius is RC. Then the orbit, the radius is RC, so we can simply take the V of R and derive it, and we end up at epsilon, let's put this called GM RC squared minus L squared RC plus 3GM L squared gamma is equal to 0, and gamma again I just put here to save myself time, so this is 0 for Newtonian and 1 for GR. And what's the condition that this circular orbit is stable? Second derivative, or it's even simpler if we're putting that minimum of the potential. So stable orbit minimum. If it's a maximum, there is still a circular orbit, but then it's not stable. It means that any small perturbation will just take you away from that.
It is something that we see in nature, like
What?
what you describe about. I mean, in this
Wait
context.
5 minutes.
Sure.
Okay. In Newtonian potential, do we have any bound orbits? Yes. Do we have any circular orbits? Obviously, yes. It's here. Is it stable?
Yes.
Yes. Fortunately for us, right? The Earth is rotating around the sun in an orbit which is very close to being circular. Right? The difference in the, I mean, we do have an ellipse, of course, but it's a very difference between the long side and the short side of the ellipse is very small. So we're very close to circular orbit.
How much?
The eccentricity of the Earth orbit, I think, 0.92 or something. I don't remember by heart. You can easily check. Just to Google what is the eccentricity of the Earth orbit. Right? We're not getting closer to the sun. I mean, some of the meteorites get very close to the sun, and you can see them. We don't. Our distance from the sun is nearly constant all the time. There are some differences, but the order of a few percent. Unfortunately for us, this is of course very stable. Otherwise, it will either fall into the sun or just drift away to space. And either way, there will be no life here. Okay. Of course, in Newtonian, Newtonian gravity. So gamma is equal to 0. Then we simply have that circular orbit appears at RC, which is L squared over epsilon G. Okay, so our radius from the sun depends on the angular momentum that we have. Now, any further questions about that?
Can I ask one general question?
Yeah.
What do you mean by angular momentum of massless particle? When you think about it, from a mechanics point of view.
It is open. Here we're also talking about angular momentum associated with the orbit of the particle. Okay, it's not the angular momentum of the particle itself. Right? We're not talking about the spin, let's say. Forget for a second about massless particle. Right? The Earth, as we know, it has several motions. It has a motion around the sun. It's also spinning, right, around its axis once every 24 hours. Right? I'm not talking about the spin. I'm talking about the angular momentum. In fact, to be precise, this is the angular momentum per unit mass, right, of a particle orbiting tension. So this is the angular momentum associated with the motion of the particle. Same. Now let's do the same for GR. So this is circular orbit using trajectories. Well, what should I do now? Let's do the same for GR. So R. This is full GR. Potential. 0, 2, 5, 10, 15, 25. This is a 0, half, 1. Okay. So it's large radii. Now I look at the full GR potential, right? Massive particles. Epsilon is equal to 1. What happens when R goes to infinity?
Looks the same. Yeah.
Look the same, right? So we go to 1. Symptotically, it's the same. Now, what happens when R goes to 0? We go to minus infinity. That's true. And where will it cross 0? Potential. It's quite easy to calculate. Just to equate that to 0. What you're going to get is that the 0 is going to be exactly at 2gm. Where R is equal to 2gm. they will simply cancel out. 2GM, this will cancel with that will cancel with that. So 2GM we get to 0. If we're going to draw that, for L equal to 1, we get something that looks like that. Of course, yes, we continue to minus the thing. That is equal to 2, we get something that looks slightly larger. That is equal to 3, we get something that's slightly larger than that. That is equal to 4, we get something like that. That is equal to 5, we get something like that. Very crudely, not trying to give you exact, but give you the general trend.
But where is the stable orbit?
Where is the stable orbit? Maybe not really important. If we want to get the stable orbit, we actually need to solve it, right? To get the stable orbit, we get the minimum of the potential. Minimum is the V over the R is equal to 0. So let's see. The V over the R is equal to 0. So what do we get? Let's simply plug it in here. What you get is that RC L squared, just giving you the final result, plus minus L to the 4 minus 12G squared M squared L squared square root divided by 2GM. So this is the minimum of the potential. So I did not draw it very well. Right, I should have drawn something that looks like that. That's okay. 5 like that. So this you can simply just do it. And when L is very large, that RC is L squared plus minus L squared of 1 minus 6G squared M squared over L squared. Just Taylor expanded that. Divided by 2GM. Which is L squared over GM and very large L, you get 2 circular orbits. One approaches 3GM here, and one is at L squared over 6 over GM. Of course, just going to be the potential. Obviously, the L squared over GM is coincides with what you get for the Newtonian one, for large L. And we have a second circular orbit, but this is not stable. That's what happens here. So you could have a circular orbit quite close to the Schwarzschild or the vector horizon, but they're not going to be stable. In fact, this is somewhat less interesting. The more interesting question is what happens where L goes down, where L decreases. L goes down, the two solutions would coincide, right? So what is the minimum value of L we can still have?
Square root of 12.
Right. So when L is equal to square root of 12 GM, you only have one solution. Right? And what is the solution? This is 0. So we have simply that RC is 6 GM. Now this is an important radius. Why? It's called the ISCO. ISCO stands for innermost stable circular orbit. Why do I say this is interesting? What do we see in nature? What happens in reality? You have some source, let's say a black hole. You know, at the center of each galaxy there is a black hole. And then there is a lot of gas that accretes around the black hole. That gas, as it accretes, does two things. Right? It will accrete in. What does it need to do? Why are we not falling into the sun?
We're falling, but
The Earth is not falling into the sun. Our radius from the sun is constant. Why don't we fall into the sun? Because what?
Velocity.
Oops.
Because angular momentum.
Because we have conservation of angular momentum, right? So if we lose angular momentum, right, our orbit will follow, will get gradually inward. Right? Now, what happens to the gas in the disk? Yeah, of course. So there's friction. Right? There is a friction. What the friction does?
Loses energy.
It loses angular momentum. It doesn't lose energy. Well, it does lose energy, but what? It gets hotter. So what happens when the gas gets hotter?
It's further apart.
It radiates. Right? So it starts seeing radiation. Yeah. Now, also it loses angular momentum. There is a transformation of angular momentum between particles of the gas. So some gets out, and some gets in. As they get in, they get even hotter. Right? Hotter and hotter, and when they get hotter, they emit radiation. And this radiation is what people can measure. Right? So the gas, so we have a situation where we have some central object, let's say a black hole, surrounded by accretion disk made of gas, which gets hotter and hotter, right? Until when? So what radius do you get in? ISCO. Right? ISCO, it is still stable. It still emits radiation, and we can still see. Now, the gas can continue to fall in. It will continue to fall in.
yes.
What happens when it continues to fall in? It's no longer stable, in stable orbit. So it can spiral. So if we look from above, right, the gas could stay like we have the whole disk here. The gas could go in, and it will fall in, but then it will spiral inward, and eventually gets falling in. So most of the radiation that we're seeing from objects, astronomers are seeing, coming from the ISCO.
Because it's like last point and
The last point
most
where it's
intense,
stable,
we can
So there is
get-
some material, but the material inside just fall in. Here, material can accumulate. So this is actually something which is measured or can be inferred directly. The ISCO, as you can see, is linearly related to the mass of the central object. So in fact, we can use that, and there are techniques of how to use that to actually infer the masses of black holes. Okay? So it has a quite important observational process. Now, actually, in the last few years, 5 years or so, more, we don't discuss the Kerr-metric here, but in the Kerr-metric there is also, of course, ISCO, but the ISCO in the Kerr-metric is different than the ISCO that we have here. It is innerwards. It's not 6 GM, but it's up like 2 or 3 GM. So people are trying to use this technique alongside other techniques, not only to measure the mass, but also to measure the spin. So this is actually something which is quite useful for astronomers that try to infer values of black holes. Okay, so what types of orbits do we have? So if we look at this potential, so we get the orbits that we have here. So we have, these will be circular orbits, obviously. I will get back to that in this space now. So we have the center of the object. These are circular orbits. Circular orbit. Of course, this is not a stable circular orbit. And this is a stable circular orbit. So again, similar to what we had in Newtonian gravity, we have bound orbits. Orbit max. Max. These will be bound orbits. Now we can think of unbound orbits. So we have an unbound orbit. What does an unbound orbit look like? So we have two types of unbound orbits now. We have an unbound orbit that looks like that. But there's a difference here because you rightfully said that when we talk about Newtonian potential, an unbound orbit would be either a parabola or hyperbola. Here it doesn't have to be a parabola or hyperbola because there is this extra term for the potential. Which means that the unbound orbit could look something like that. You could have a situation where we have a particles come in, so we rotate and move out. That's a possibility. And then of course we have a situation of unbound orbit that goes like that. Of course, this is something again that does not exist in Newtonian physics and Newtonian mechanics. How would an orbit like that look like? No, it doesn't have to
Oh, you mean to the curvature of space?
Or something like that. And then
Oh.
Because remember, we're only looking here at R. We
Yeah.
don't look at theta or phi and tau. Yeah? Where's it here? So we basically have, and to summarize that, so the following that we have stable, so summary, stable circular orbits exist for R, which is larger than 6 GM. Unstable circular orbits exist for R, which is in between 3 GM and 6 GM. Again, but one more thing to remember, these are only geodesics. So in principle particles, if you accelerate them, if they don't move along geodesics, right, they can get less than 3 GM and still get out as long as they don't enter the short range. So as long as they go. So there's nothing that prevents, in principle, particles from moving to 2.5 GM and back. But then you need to have an acceleration. It will not be able to do this. Okay. Okay. Any further questions about that?
Then scientists talking about this type of gravitational maneuver, then you can accelerate the starship by going around some planets or satellite and go, for example.
Not sure that I'm with you.
Like they did with the James Webb telescope, or that it's orbiting some.
No, I mean, then
When you talk about something which got nothing to do with GR, when you're talking about a planet that is moving, let's say this is a planet, let's say Jupiter, moving like that. Now you take a spaceship, the spaceship is going like that, but then when it gets to Jupiter's gravitational potential, you do something like that. That's what you do. It will be rotated by the...
Yeah, but does it accelerate the ship or not? Because sometimes I heard that people use it like
yes, it does. It does, because what happens is that you can think of it like that, right? It had momentum in this direction. Jupiter has momentum in this direction. Now it has momentum in that direction. Momentum is conserved, obviously. So momentum was lost by Jupiter's orbit. But this is just simply a transformation, you know, because Jupiter is using the fact that the planets are moving in relative to the sun. So basically it took some energy from the Jupiter's orbit around the sun. If you did it very low, you know, very heavy, then eventually it would cause Jupiter to fall into the sun. This is completely classical, so nothing to do with GR. Okay? But this is simply transformation of frames. Classical ones, nothing to do with the Lorentz transformations. Okay, let's move on to our, what am I doing with the time? Let's move on to massless particles, namely photons. These are trajectories of massive particles. So, massless particles. Perhaps it's photons. It doesn't have to be photons, but it's the most important one. So that's pretty simple, right? Everything we need to do is just put epsilon equal to 0. Get V of R. 2 minus epsilon g f of r plus m squared 2r squared minus g m l squared over r cubed. So we just put 0 here. Get the very simple potential. And of course, in the Newtonian case, we only have that. So for Newtonian, something which is very simple. This is R, this is V of R, and so we put 1, 0, 5, 10, 15, 20, 25. Of course, everything is normalized to GM. I've mentioned that, but also here the units are. So of course here the potential looks very simple. We have one term. This one. So when R goes to infinity, it goes to 0. When R goes to 0, then it goes to infinity. semicircular orbits here, bound orbits. No, right? What are the only types of orbits that there are? Open and okay, it's a bit more difficult to see that from here, right? But don't come, you go back. How does the trajectory really looks like? Photon in Newtonian potential?
It looks like the program.
Talking about photons in Newtonian potential. How do photons move in Newtonian potential?
Straight lines.
Straight lines. Right? And the only way to move is like that. So why do we say it looks like that? Because we're only looking at R of gamma, right? So if you measure R, so it comes from infinity, so this is lambda, R of lambda. Right? So lambda decreases, so R decreases until you reach the point of closest approach, and then it goes back. Okay? Don't get confused. This is how photons move like in a Newtonian gravity. Photons don't get of course, R is sort of slowing down. Of course, they're not really slowing down. Just moving at the same speed of light. They're not changing their energy. And what does the difference L's means? So the smaller the L is, the closer they will get. So if you have smaller L, that means that it simply corresponds to the relative angular momentum that basically answers your question. And if you have smaller L, that just means that they will go closer to the source. It's an angular momentum associated with the trajectory, not with anything else. Of course, if L is equal to 0, then they just get central object. Now let's do the same for GR. So if we do the same for GR, let's use that. This is for massless particles. Zero to GR. What does the potential look like now?
There is a closed circle.
Alright. Let's ask first, what is the potential? How does the potential look like?
If R goes to infinity, potential goes to 0.
So when R goes to infinity, potential goes to 0.
Yeah. Then
What happens when R goes to 0?
minus.
It goes to minus infinity, and at which radius do V of R is equal to 0? Schwarzschild. L squared, L squared. So when R is equal to 2 GM,
Yeah.
right? So when R is equal to 2 GM, it goes to 0. So if I look at the potential will look something like that. This is L equal to 1. L equal to 2. L equal to 3. So on and so forth. Etc. Right. So again, what type of trajectories we have? So first, there is always a barrier, unless L is equal to 0, meaning that the particle just moves straight into the source of potential. There is always a barrier. Then again, if the photons are energetic enough, they could always cross this barrier. what happens if a photon is not crossing the barrier? So like that, and like. What would the trajectory look like? No?
Now we will look at parabola.
It's not exactly a parabola. It cannot be exactly a parabola, but it will be tilted. Right? What really happens is the photon will come from infinity and then be tilted away. You know how we call that?
Push.
Yes, gravitational lensing. This is exactly gravitational lensing. Right? Remember this picture that I draw, right? That you have this. So the photon trajectory will go something like that. It comes from infinity. Again, it moves in straight lines. Geodesic, of course, right? But the space-time is not curved, so it will be curved. Right? And then, if it's sufficiently energetic, it can always cross this barrier. So what will the trajectory look like? What?
All into the singularity.
Exactly. Just be following the singularity. And of course, here there is also a possibility of being at the top of the potential. Right? Where is the top of the potential? So for epsilon is equal to 0, which is the top of the potential. So dV over dr is equal to 0. Do the calculation, you get 3 here and you get 4 here, so you end up that RC is 3 GM. Down. So 3 GM, you do have a circular orbits of photons. Very strange, but they exist. Let's have a situation. Photon trajectories that just spiral, exactly like that. But do we expect them to do we expect to see anything? No.
They are
Why not?
unstable.
Yeah, they are unstable. Right. So any small perturbation will immediately take you either spiral outward or spiral inward. So we don't really expect to see a big signal from it. But mathematically, the signal exists. This is for any value of error. So I cancel some. Okay. Further questions? Oh, my goodness, that actually we're slower than I was hoping, but I think it's okay. We won't finish the next subject today, but we can take, I think on Thursday, what we might do, we'll complete what we're doing now, and then we will have a tutorial about precession. This is important enough that I think you should know it, if nowhere else at least. So the next subject is called classical tests of GR. So, we spent the whole semester, or most of it by now, telling you all sorts of very nice mathematical stories and developing a big theory and big equation and you finding the solution. that equation and discussing what we may expect to see. Now, of course, this is the Department of Physics here, not of mathematics. So what we really care about is understanding nature. And obviously, if this theory would not represent nature, it would not be taught here, maybe in the math department, not here. So, of course, Einstein introduced this theory, but before people could accept it, it has to be tested, and checked, validated. So there are several, actually there are four, there are 5 independent tests of general relativity. This is the time we talk about the classical tests. So we won't have time to discuss both of them. We do have enough, we do know enough by now to explain you, and then the rest of the details, the mathematical details of things you can fill in by yourself. So we're talking about experimental tests of GR. So what experimental tests you can imagine? Right, so yes, right. Take yourself backward 100 years, okay? By the time of Einstein. Einstein wrote this in 1950. Then, when he wrote this theory, he already thought of what could be possible tests for this theory. So, actually, I thought of 3. And then there's a 4th and a 5th. So one we say reflection of light, but how can we test reflection of light?
No, if I see a star where it should be, if there is a star where it should be in the present gravitation field, and we see it in a different direction.
Where do you see the gravitation? How do you know where a star should be and where is the present gravitational field?
The closer the gravitational field is the sun, and it should be like
how do you know where a star should be?
That's a good question.
Okay, so you can think of how you get it. So, but this is true. This is called deflection of light by the sun. Other tests.
We already talked about relativity.
What?
Relativity.
Precession of Mercury, yes. So precession of the perihelia of the polar planet. Perihelia is the point to say that all the planets are going in ellipses, in slight ellipses. This is known as Kepler's lines. And perihelia is the point of where it is closest to the sun. So perihelion and up, closest. Yes. Or independent test.
Maybe some sort of experiment that we can conduct on Earth.
Which one?
We talked about the Doppler shift gravitation.
Yeah.
So gravitational redshift. We don't need to do there. We have spectral lines. Spectroscopy was known 100 years ago. So gravitational redshift of spectral lines. Right, we know that the sun contains hydrogen and helium. Through spectroscopy, you can actually see them. You can measure the redshift of these lines. So in fact, you're right. These were the 3 tests that Einstein himself proposed as a way of testing his theory. Since then, we know 2 more. One you know, and one you might know. Actually, one I don't expect.
Black hole.
Tests of what?
I mean,
What are you testing?
the theory predict.
How do you test? That's something. Test is something which you can experiment on. Some experiment which you can do.
Gravitational waves.
Gravitational waves, of course. Gravitational waves. gravitational waves. So this is something which was also suggested by Einstein, but he did the calculations and he realized that these are extremely small signals. So he anticipated this could not be done, and indeed it took 100 years until the technology had developed such that this experiment can be done, and it was conducted the first time in 2015, so 100 years after gravity, after the gravity, and to build the machinery took about 4 years. Machinery is actually very simple, just extremely accurate. The first one is something which I don't expect you to know. It's called a Shapiro time delay. It's a time delay of a signal that passes through the nearby gravitational potential. And it's called by Irving Shapiro, which you happen to know in person. The guy is still alive, should be around 90 today, alive and kicking, and every time I meet him, which is not that often because of the war recently, he asks me questions I don't know how to answer. So it's called the Shapiro time delay. Which is a gravitational time delay of a signal, weather signal, signal sent in the presence of gravitational potential, I should say.
It's very related to the first one.
No.
Why?
This is a redshift of the lines. You're seeing the spectroscopy. This is something else. This is the delay of a signal. You're sending a signal, and it's reflected back, and you're looking at the time delay relative to the expectations of the Keplerian motion.
Light is also
And
you can invert
it's
frequency
the same. It's
to
the same
time
equation.
and
No. Okay, let's discuss that and you'll see what happens. Right? No, it's not the same thing. This is gravitational redshift of spectral lines. This occurs when the source and the detector are not at the same location. Right? The source of the spectral line, the emitter and the detector are not at the same location. The same Alice and Paul. Here, the time delay is a signal that we on Earth are sending to, let's say, Venus, reflected back to us. So we're standing at the same location. We're not changing our location. Okay? And we're measuring the delay in time that the signal arrives relative to the expectation from a Keplerian motion, to a Newtonian potential. There is a delay. I'm going to derive it to you briefly, so you'll see. So, if the emitter and the observer are located at the same location in the gravitational potential, there will be no redshift. This is a delay because we're sending a signal and it comes back to us. And the delay is relative to what we'd expect it to be in Newtonian potential. Okay. If at all, this is more related to these two than to that one. Okay. So these three were suggested by Einstein himself. The first experiment that was actually done, do you know which was? Eddington. This is this one. This was the Eddington. This was 1919. Well, this can be considered as a prediction, post-diction, in other words, because measurements of Mercury's orbit, accurate enough measurements of the Mercury orbit, existed already in the 19th century. From 1850 or so, they were accurate enough that people could tell that there is a problem, that they don't match exactly the expectation from Newtonian gravity, and Einstein managed to solve that. And before that, people didn't know exactly. So data was accurate enough, so this could be considered as post-diction. This is a prediction, which was the first to be tested. This was the second. Shapiro time delay was suggested by Irving Shapiro in the 1960s, and was conducted at the early late 1960s, early 1970s. And gravitational waves, of course, was predicted by Einstein in 1917 or so, but logically this was detected only the last 10 years. We had to wait for 10 years. Right? Okay. Cool. So what we're going to do, we're going to I guess we can stop here because time is running out. Then what we'll do in the next time, I will explain to you, so we'll go over definitely this one in details, this one in the other ones with some partial details of this, so we can see the idea. By now you should know it, you're just looking at the metric and doing integration of trajectories along this metric, basically. This one typically I will not discuss because this is it's a full section by itself, but it will take something like 3 weeks to cover that properly. We'll may say some things about that towards the end of the semester. But really this is a chapter in a book which you can simply open and read once you have basically by now you should have everything you need for that. Okay. So I think this will be covered and we'll do that on Thursday. Any questions? No? So good luck. We'll see you on Thursday. So Thursday, the plan, my current plan is to split, to make 1 hour maybe we will discuss about classical tests, and then the rest will be tutorial.